kind introduction. It's a real honor to be here, right? So to present some research results, right, in this very prestigious workshop, right? I hope everyone is doing as well as possible, right, despite some of the ongoing challenges. Okay, so today I want to talk about some of our new research results on HLS or hydrosynthesis for hardware accelerator design, and also I want to share some of my personal view on this topic. So in my mind, I really think that this is probably one of the most exciting times, right, to work on hardware specialization or specialized computing, right? Because it's clear that we have very strong demand, right? So to accelerate many different kind of very compute intensive, also very data intensive workload, right? With the CPU scaling getting really flat, right? We need something some new hardware which is much more efficient, right? So in terms of energy consumption, also in terms of performance. And also at the same time, I think it's getting a lot more affordable now, right? So to do specialized hardware design. So, with these new cloud FPGA platforms becoming available, and also with this new open source hardware movement, right? So, all of these are really making the hardware specialization a lot more, a lot cheaper and also a lot more fun. Okay, so I really think this is sort of one of the best of times, right, to work on this topic. At the same time, I also argue that this is probably one of the more challenging times to work on this topic as well, right? Because of the target of specialization, the target applications are actually changing pretty rapidly. Right? If you just look at the citation count, right, of some of these, most famous deep learning papers, right, in recent years, you can probably already get a pretty good feel of, right, how fast new ideas, new algorithms are popping up, right, in just one specific field. And for some of you who are actually familiar with this topic, right, you may actually think that, these numbers sort of, appear kind of low, right? So indeed, it's actually, I took the snapshot 2 years ago, right? If you look at the latest numbers, right, so they easily, quadrupled, right, for some of the papers. So this also gives you a sense of how fast, right, sort of velocity of the change in the application field. So with this in mind, I think it's fair to ask the question, is RTL-based design methods still sustainable, right? So can they keep up with the pace, right? Although they are still sort of considered as a mainstream. Okay. So, with these challenges, right, so we're actually really seeing the renewed interest or resurgence, if you will, of HLS or hydrosynthesis. So I'm actually showing a flow. This is the flow of one of the HLS tools that I got heavily involved with, right? So initially it's called Autopilot. So being developed at IWLS20, later got acquired by Zhang, was renamed to Vivado HLS. I think the latest name is called Vidas HLS. So with a flow like this, there are actually many obvious advantages, right? You get high code size reduction, right? Get simulation speed up, right? You can do design reuse more easily. And of course, right, design space creation more easily. Okay, but usually when I present flow like this, right, tool like this, so people usually ask, right, as a few years ago, so the first two questions they will ask, like, can HLS actually handle complex designs, right? And also, can HLS really compete with hand-coded RTL in terms of QOR or quality of results? Okay. So I just want to show you some evidence, right? So this is actually a study done by Zhang a few years back. So they look at the design called memcached. This is basically an in-memory key value store, right? So this is actually a fairly complex design because it's has interface memory controller, also network interface with quite a few different blocks, right? So actually the code is open source. You can take a look. It has non-trivial complexity. So what they found is actually they implemented the orange blocks in HLS. Right, so they also have very experienced RTL designers, really RTL expert, who implemented the same design using Verilog in this case. They compared the both resource usage and also performance, right, head-to-head, HLS versus RTL. So interestingly, so in this case, HLS is actually winning in terms of both resource usage, right? So this is targeting FPGA using Vivado HLS, right? So if you look at different blocks, right, so HLS offers smaller area. If you look at the latency or cycle count, right? So compared to RTL. So, with the automatic scheduling, with many optimizations. So in this case, HLS also outperforms the RTL. So which is actually very encouraging news. Okay. And this is an industry study, right? Of course, I don't have the market data, from the, the vendors anymore, right? But if you just look at academic usage of HLS, it's also showing very encouraging sign, right? So this is we basically search this keyword, right? So we just focus on IPJ, right? In this specific case, you can see that initially the use of HLS has been pretty flat, right? But recently it's really picking up, right? Of course, because of some of the more viable solutions are now available, right, from both Intel and Xilinx, and also ASIC Cat2 vendors, right? So some of them can target FPGA as well, and also because of the demand for deep learning acceleration, right? If you look at the numbers, so from the date, right? So the paper that I showed you, or the study was 2014, right? After that, we are seeing almost like 10,000 papers now. So actually, even this number is not up to date. So this is, we took the screenshot, a few days ago. Okay, so this is a really encouraging news, right? So with this in mind, right, I also want to point to you can also just search on GitHub, right? Like just look at what kind of open source RTL blocks or Verilog blocks are available compared to the kind of HLS open source project that are available on GitHub. It's going to be immediately clear, right? What kind of complexity, right? So you can do with RTL, right? And what kind of complexity you can afford with design complexity you can afford with HLS. So with this in mind, right? So it's fair to ask this question, right? So have we finally solved HLS, right? So in theory, right? In practice, or in style, right? Is it solved in the right style? Okay, I'm gonna explain what I meant by style. And also, I put double quotes on this, right? Since these terms are heavily overloaded, right, in my presentation as well. So I'm gonna, for each question, I'm gonna elaborate. So with some of our new research results, right? So in here, for the first part, I'm gonna talk about a new sketching algorithm, and then for the second part, I'm going to talk about the QR estimation for HLS. And also for the last one, I'm going to talk about a programming model. Okay, so I'm going to start with the first one, right? So I'm going to delve into the sort of HLS theory first. Okay, so by looking at the very core HLS optimization problem, which is scheduling. I'm going to talk about the algorithm called SDS. This is a joint work with my former PhD student, Steve Dai, and also Guy Liu. I believe Guy is also one of the organizers of the IWLS programming context. Okay, so real quickly, I know many of you are already familiar with HLS, right? But really quickly about HLS scheduling. So this is one of the key steps for HLS, since this defines the clock boundaries, right? This insert register boundaries in an on-time design. So which has huge impact on the quality of the synthesized RTL. So for example, if a very simple example, like a chain of 3 additions, right? You can chain them together in one cycle, very computationally to really optimize latency, or you can insert registers, so you can schedule things in a sequential way to optimize the area, or you can make it fully pipeline, right? So to maximize throughput, right? So this is what scheduling can do. You can immediately tell, right? So this has a very direct influence on the final performance also, of course, area. Okay, so because of the importance, right, this is a heavily researched topic, right? If you look at some of the papers I'm listing here, right? So, this is dated 35 or even 40 years back, right? But in general, so there's actually tension between the scalability and quality of these algorithms, right? Now, of course, you can formulate everything as ILP, right, or mixed integer linear programming. So, to get high quality, right, with respect to a certain given objective, or you can use different kind of heuristic, right, or including some very fast one like the scheduling, right, which is more greedy, or you can do meta heuristic, right? So there's different trade-offs, right, between this these two important metrics, scalability and quality. But really the question is, can we get the best of both worlds, right? Can we get both high quality and also high scalability, right? So can we also handle rich set of constraints? Okay, so this is really the research question that we are asking. Okay, so if you look at some of our recent results, I'd like to start with this STC-based scheduling first, since this is also going to be the foundation of the new algorithm that we're going to introduce. So STC-based scheduling is actually being used in many of the current commercial HLS tools, also academic open source HLS tools. Okay, so I'm not going to give you the sort of full intro of STC. So you can view it as sort of extension of generalization of retiming. Okay, so if you look at this is a simple data flow graph, right? We have 3 memory loads, right? So additions and memory store, right? I have some timing, right? Estimates, right? Delay estimate associated with each node. Okay, so the way we formulate SDC is for each node, let's say, we come up with a variable, let's say T sub I, okay? So this basically sort of roughly indicates the time step, okay, of each operation after scheduling. This can be generalized to control data flow graph, right? So that's where, this T has different meanings, slightly different meanings, okay? But just real quick, so with SDC, we actually use these schedule variables to formulate a set of pairwise difference constraints. So in this case, so if you look at this constraint, this is actually models a dependence constraint for this specific data dependence edge between operation V0 and operation V4, right? So if you look at this inequality constraint, it basically says that operation 0 cannot be scheduled after operation 4, right? As simple as this, okay? Right, and actually this constraint also naturally support operation chaining, right? These two operations can be scheduled inside the same clock cycle, but again, 0 cannot be scheduled after 4. Okay, we can also handle other constraints like cycle time constraints. So let's say we target the 200 megahertz design with 5 nanosecond cycle time constraint. In this case, right, if you just take a very simple, right, added delay model, although this is the wrong model to take, right? I'm gonna get to this, right, in the later part of my talk. But let's say we just add up the delays, right? This is gonna be a critical path, right? That's exceed the cycle time target. So this is where we have to insert register somewhere, right? We either have to, put it here, or in the middle. So we have to break this long path, right? So this is where we insert another pairwise difference constraint like this. So this basically says that operation V2 must be scheduled from away from operation V5 by at least 1 cycle. Okay, so this is what the -1 means. Okay, so basically we want to insert at least 1 clock boundary, 1 register boundary along this path. Okay, so this is sort of SDC in a nutshell, right? We can actually use it to extract other constraints as well, including resource constraint in a heuristic way. And there are actually many benefits of SDC. So, we can, since the underlying matrix of this constraint system totally unimodular, we can actually, just use linear programming to provide integer solution. And another benefit, again, this is probably well known to many of you, right? So with a system of different constraints like this, SDC like this, we can easily translate it into a constraint graph. Okay, so over here, basically each variable corresponds to a node, and then each constraint corresponds to an edge. Okay, one of the nice things of forming this constraint graph, you can easily check the legality or feasibility of this SDC system. So in this case, for example, it's actually not legal since you look at these two constraints, right? So they sort of contradict with each other, right? If you just sum up the left-hand side and the right-hand side, so we have a contradiction. So this can be easily captured on the graph if we solve a single source shortest path problem. So we can easily identify the negative cycles like this. Okay, so hopefully this is clear, right? Feel free to stop me, right? Since this is, I'm going to cover many different topics, right? So if you have questions, just let me know. All right, so this is SDC, right? But there's a more difficult constraint to handle, which is resource constraint. Again, same example, right? If we only have 2 memory reports, but we have 3 memory loads here, right? So we have to serialize some of this, right? So let's say we have to decide to serialize V0 and V1, right? So then we may actually end up with, depending on how we serialize it, right? Whether low 0 is before low 1 or low 1 is before low 0. So we're going to end up with different schedules with different latency, right? So in general, so this is actually a hard decision to make. So in general, this problem unfortunately is NP hard. Okay, so resource constraint scheduling problem is NP hard. Okay, and also in the SDC form, it's actually more difficult to handle this since you want to serialize these 2 operations, right? We really want their time steps or schedule to be different, right? They cannot be scheduled in the same clock cycle. Okay, so this translates to something like this, right? So which is not exactly in the form of SDC. Okay, so again, there's heuristic, right? That we can basically pick one of those. Okay, so that's where the suboptimality comes into the picture. Of course, there is a more rigorous way, right? So more exact way, an exact way to handle this, right? Using Boolean formulas. Okay, so basically over here, if 0 and 1 share the same resource, so this is one Boolean variable, it's going to imply that. So I'm going to introduce another Boolean variable over here. So this means that 0 is scheduled before 1, right? If this Boolean variable is true, okay? Or so the other Boolean variable means that operation 1 is scheduled before 0, okay? So again, if 0 and 1 share the same port, then either 0 has to be scheduled before 1 or 1 before 0, right? So we can capture this in an exact way, right? Using the Boolean formulas. All right. So with this in mind, so I'm going to introduce the overall framework of SDS, right? So we have actually combined the formulation of SDC and also set. Okay, so we use SDC to capture the timing constraints, okay, and we use set to capture the resource constraints, both in the exact way, and we're going to make them learn from each other, okay, in the SMT like conflict-driven manner. Okay, so basically, set is going to propose ordering, partial ordering between operations, which is going to be converted into difference constraint in SD form. SD form will actually detect invisibility and then generate additional conflict clauses. So by doing this, we actually exploit the efficiency of SDC, right, for for this feasibility tracking, right, using graph-based algorithm, and also we really hope to exploit the scalability of modern set solvers, right? So that in practice we can solve the resource constraint scheduling problem in an exact and also scalable way. Okay, just want to make a note that I'm actually using a very simple example, right? So pure data flow graph without pipelining. Actually, all of this can be extended to handle control data flow graph with more complex resource constraints and also pipelining as well. Okay, so so just want to give you a quick example, right? So this is the same data flow graph. Okay, again, over here, so this is basically a set of a resource constraint right, specified in Boolean formulas, right? So the way that these two systems interact is, so first set solver is going to propose, right, a set of orderings, right? In this case, right, so 0 is before 1, 0 before 2, 1 before 2, right? So which is going to be translated into new directed edges, right? So in the SDC constraint graph. So actually, there's a very efficient algorithm to solve this in an incremental way. So where we can detect the negative cycles, okay, in the SDC. In this case, right, there's actually a conflict. Okay, so there's one edge that makes the system illegal, infeasible. So we're going to convert it back into the set formula, right, Boolean formula. So over here, then we add it back to the stat system. Okay, so this is what I mean by this is conflict-driven learning, right? So over here, what the set learns from the SEC is, so any ordering that involves between operation 0 and 2, right? So if 0 is scheduled before 2, so that should not be attempted anymore. Okay, so that immediately prune away a lot of the solution space. Right? So we can keep doing this. So then next round, right, so we will propose a new set of assignments, right, which will also cause some additional conflicts, right, in SDC. So that will also generate additional clauses to set. Okay, so so if you keep doing this, right, eventually set is going to propose a new assignment that makes the whole system feasible. Okay, so this is where we can return a legal schedule. Right, hopefully this makes sense, right? This is really we are making use of the efficiency of both set and also the graph algorithm. So just want to show you some results. So with SDS, we first run the classic resource constraint scheduling algorithms, right, on a set of data intensive data flow graph benchmarks. These are common HRS benchmarks, and compared to ILP. So both commercial ILP solvers and also open source ILP solvers, you can get very high speed up, right? In some cases 2 to 3 orders of magnitude speed up. Right? Of course, in some cases, right, the large benchmarks ILP will time out. Right? Okay, so and I'm just showing part of the results, right? There are also quality comparison on quality with heuristics, right? So of course, so since this exact, we are winning in terms of cycle count. like I mentioned, we can also further extend it to handle pipelining as well, right? So in this case, we also compare with the default ILP formulation for pipelining, module scheduling, and also some of the latest, right, ILP formulation, with a lot of different optimizations to really reduce the number of constraints, also the problem size. So again, with a SDS-based approach, in this case for pipeline, we call SDS plus. Again, we are much more scalable compared to ILP, right? Again, we can get, in some cases, much 300x speed up, right? So we can really solve the problem exactly within a split of seconds in most cases. Okay. So we are actually pretty excited about this result since this is not just specific, right? So the scope of this algorithm is not just specific to HLS, so applies to many other optimizations, scheduling optimizations, right, in other fields as well. All right, so this is the first part, right? Okay, so I just talked about a new scheduling algorithm that solve a core HLS sort of theory. Okay, once it's a core HLS theory, right? So to be more precise. Okay, so but with this new algorithm, right? So suppose we can solve complex optimization problems in seconds, right? So does that make HLS a lot more usable in practice? Right? So let me then move on to the second topic, right? This is a joint work with my student Steve, right? Yuan, Ajay, Chenhui, and Debjit. So this is where we actually look at how accurate is the HLS QOR estimation, right? Of course, we can solve optimization problem very efficiently, but that optimization problem actually assumes certain models, right, in terms of a delay and area. Make assumptions, right, on those models, right, on the estimation of the area, and but how accurate are those estimations? So that's really the question, right? So ideally, right, for example, for FPGA-based acceleration, right, with HLS, right, so this is the latest flow. Now that we can solve complex problem in a very fast way. So ideally, we don't want to always go to go through the downstream optimization, including place and route, since this is just too slow, right? It can take hours to days, right, to get the final area and timing results, right? So ideally, we really want to iterate over here, right, as fast as possible, as often as possible. But really, the question is, can we trust the QOR estimates, right? Can we trust area estimates, right, or timing estimates from HLS? So this is where we did the study. So on many open source HLS benchmarks, right, we collected 65 designs from 4 different open source benchmark suites. Okay, so these designs have different characteristics. You also target different clock constraints, also different FPGA devices to generate more samples. Okay, in this case, we are looking at VBottle HLS. This study is done 2 years ago. Okay? And and then we compare the results against the final close place and route implementation results. Okay, so surprisingly, we actually found that the estimation from HLS is very off. Okay, so this can be off by up to 4x in some cases. Okay, so actually the mean is for lookup table estimation and flip-flop estimation, it's easy 2x, okay, according to our study. So this is worrisome, right? So that means that we still in practice, right? We still need to go through the full synthesis, full place and route, right? If you actually want to get some meaningful estimation, we cannot really trust the HLS results. Okay. So this is where we start to look at machine learning, right? So what if we use there are actually many interesting data, many interesting stats from the HLS reports that we can make use of, right? So of course, right, they estimate the different kind of resource usage, right? They also actually provide a very detailed list of the number of inputs in the multiplexers and how many adders do you have, how many multipliers do you have, the BRAMs and everything. So this is where we actually collect them, right, into a rich set of features. Okay, so we have 87 features in this case, and we feed them into ML machine learning models. Okay, so that of course we go through training, right, and then we for a set of designs, and also we tested on a new set of designs. So we actually tested this approach with several machine learning model, including linear model, neural net, simple neural net, and also XGBoost. Okay. XGBoost actually turns out to be very useful and very powerful. Okay. So with this approach, we can actually dramatically reduce the error of the estimation. Okay, so from it's on average like 160, right? So this is measured in terms of RRSC, a relative root square error, right? So 160, right, which is 1.6, right? So this is really, really high. So down to it's 20 to 30, 0.2 to 0.3, so which is much more reasonable. Okay. And also, like I mentioned, right? So in this case, we actually found that gradient boosted trees is one of the more popular. It's actually one of the more popular framework being used right in data analytics. As it turns out to be very useful for learning categorical data, learning from categorical data. Okay, so this is for resource estimation. Okay, we call this approach quickest. It's actually give us a much higher confidence, so with this, so in terms of the final area estimation. But of course, we also need to ask, right? So what about delay estimation? So which is even more challenging, right? Especially considering all these DSP mapping, right? Lookup table mapping, and other physical design steps. So also with quickest, we only look at the reports, right? So there we don't really have the graph, HRS graphs. So I just want to quickly mention a new paper that's coming up at ICCAT. So this is where we are making use of graph neural networks, right, or GNNs, so to actually get better estimation, a better handle of the delay estimation or delay categorization for HRS. So this is where we actually take advantage of the graph structures of the topology. Of course, we also need additional information right now, what kind of operations we have to build with and everything. With this approach, we can actually train graph neural nets, which give us a much higher accuracy in terms of whether certain operation, right? Plus and this plus and multiply are going to be mapped to a dedicated DSP blocks or not. Or this plus, right? These two plus, right? These two adders will be clustered into carry chain, right? Because these actually have a very large influence, very large impact on the delay estimation, right? If you think about the simple model that I showed you, right? So there I simply just add up the delays, right? Which is totally not accurate, right? So ideally, so we really want to and sort of a guess, right? What kind of decisions RTL sensor mapping will make, right? Based on the different kind of structure in the graph. Okay, so if you're interested, right, check out our upcoming work. So which is going to be published at ICCAT 2020. Okay, so I just covered two topics, right? Just talk about the new scheduling algorithm, and then also talk about how we can make HRS QOR estimation a lot more accurate. So next, I'm going to talk about whether we have the right style, right, of using the HRS tool, right? So by style in this case, I really mean a programming style. So this is where I'm going to talk about one of our new framework called HydroCL. So this is actually the FPGA best paper award last year. This is a joint work with my student Zhang, Shao Jie, and also UCL student Yuzhe Jie from Professor Jason Kong's group. Okay. So the key idea behind HydroCL is we actually want to decouple the specification of algorithm and the hardware customizations in HRS. Okay, so this is a real quick overview of HydroCL. So this is actually a new programming language. We call it intermediate language. It's a Python based. So we want this language, also a compiler framework, to be productive. So it's easy to program. With a Python interface. Also, we want to support high-level DSL as well. So we also want it to be very efficient. We wanted to generate highly competitive QORs against the expert. Also, another important thing, we want it to be portable. Okay, so we actually want to decouple the algorithmic specification from hardware customizations. Okay, so in this way. Okay, we actually want to decouple, algorithms in either declarative programming or imperative programming style with three important types of a customization technique. What we call is compute customization, data type, and memory. Right. So what do I mean by this? Okay. So just a really quick clarification of the terms. So if you look at the essential ways, right, essential techniques that we do hardware acceleration. So really. So when we try to speed things up, right, we actually want to run as many compute engines, right, as many compute units as possible, right, by either doing unrolling, parallelization, or pipelining, right. So this is where we are exploiting the parallelism. So this is what we call compute customization, right. So these techniques, okay, and also in many cases, right, even this is not sufficient, right. So we actually want to run even more things in parallel, right? With the same silicon area, with the same amount of resources. So this is where we can actually exploit the trade-off between efficiency and precision, right? By using like low bandwidth integers or fixed point types. Right? Okay, so this is what we mean by data type customization. Of course, the next obvious challenge, right? So is how do you feed these bits, right? So how do you make sure that we have enough data, we have the sufficient data, right, to keep all of these processing engines busy. So this is where a traditional general purpose memory hierarchy will not be sufficient. So we have to make use of memory customization techniques, right? So like banking, data reuse, the streaming, right, to really take care of the data placement, to really optimize the locality. Okay, all right. So this is what we mean by the three major type of hardware customization techniques. So with HCL, actually with HLS, so we can actually specify, right, all of these techniques. HLS is already becoming very powerful. Okay, so using the high-level programming language, like in this case, I'm showing IWLS20, right? You have the pragmas, right, to do compute, right, the pipelining, or you can also do tiling by hand. You can also add these special data structures or classes like APFix to customize data types, or you can specify the on-chip memory reuse buffers, right, like line buffers or window buffers using these special construct like from offered by the HLS tools, right? But the one thing is, the moment you specify all of these optimizations, the code is no longer that readable, right? It's not that easy to tell what's going on anymore, right? So for HLS expert, you can probably initially tell. So this is just a convolution. It's just a simple convolution, right? Although like the code already looks very convoluted, because right, so we are actually entangling the algorithm specification, right? So with many of the hardware customizations, right, in the same spec. So this is really what I meant by this is really not specified in the right style. Okay, so with HCL, what we want to do is we really want to decouple this too. So HCL is actually inspired and influenced by early DSLs like Halide, okay, so which is targeting image processing for CPU and GPU processing, and also later on TVM, right, which is now a popular DSL for deep learning. So what we want to do is we also want to decouple the algorithm from the optimizations for hardware specializations, especially for FPGA-based compute. Okay, with HCL, again, this is a Python-based DSL. We can actually support both declarative programming like this, right? In this case, we are actually using lambda functions instead of explicit for loop nest, right, to specify the convolution kernel. In this case, we actually reuse some of the syntax from TVM. Okay, and also the compute customization is completely decoupled, right? You don't have to insert pragmas. You don't have to interchange loop by hand. Instead, we have a separate section of code to specify how we want to parallelize things. Okay, for example, in this case, we can do unrolling. And also the data type specification also completely decoupled from the algorithm spec. Okay, so we assume that algorithm spec has the full precision, let's say, and then we can actually make use of this additional primitive called quantize. We will have something called downsize, to really, for example, to quantize the floating point types into fixed point, right? arithmetic, right? Whether it's 32-bit, we actually support arbitrary precision. We also support arbitrary precision for blows, fixed point, and also integer using these primitives. Okay, and in the, this is actually new, right? This is not provided by any of the existing DSLs, including Halide and TBM, right, which provide this kind of decoupling. So in addition, so we take one step further. We further try to customize, decouple the memory customization. So in this case, again, you don't have to manually insert those line buffers and window buffers, insert those additional classes, right, in your code. You just need to specify, right? So since we are doing a convolution, right? So we are moving in this case 3x3 or 5x5 window, right, across the image grid. So we can actually specify, like, I want to do data reuse, for example, across Y dimension or X dimension, and the compiler, hydroxyl compiler, is going to automatically infer the right kind of on-chain memory buffer for you. Okay, whether it's a line buffer, so in this case, then we do the data reuse across Y dimension, or when we do the data reuse further across the X dimension, we're going to infer to the very efficient flip-flop based window buffer for you. This is SRAM based. Okay. So all of this, right, the details are completely hidden, right, from the user. So basically, this section is actually programmable. Okay. So just not just pragma, you can actually write for loops as well to really efficiently explore the design space. Okay, so this is really, a hydroxyl in a nutshell, right? We actually provide many useful primitives, right? So for compute customization, data type, and memory, and also in many cases, right? So if users already know that they are dealing with, for example, a stencil program, right, or a systolic algorithm, they don't have to use, a long list of a combination of these primitives, right? Instead, they can just specify, we call it macro. So, I want to map it to efficient spatial architectures, like for stencil data flows, or I want to map it to systolic arrays. Okay? So with just one macro instead of using a combination of many primitives, micro primitives. Okay, so this is our compiler. Okay, we can target different FPGAs, embedded or cloud FPGAs, both Intel and Xilinx. We are making use of the IWLS tools. Okay, underneath. Okay. We are also making use of some of these efficient backend to generate efficient spatial architectures like PolySA and so that. These are from Professor Jason Conscript. Okay, we actually can integrate additional backends, right? So for different kinds of spatial architectures. Right, I just want to show you some quick results. So with hydroxyl, we can generate fairly efficient hardware for a different kind of applications. So for example, for stencils, we can get pretty high speed up, right? On Amazon, this IWLS20 compared to optimized Intel CPU code. So in this case, I'm not showing the resource usage here, but just want to show that indeed, so we are already reaching the limit, right? So that defined by the memory bandwidth bound. Also, we can generate systolic, right, accelerators efficiently. Again, comparing to optimized Intel MKL code. Okay, this is for matrix multiply or deep learning kernels. We actually first support imperative programming, although I don't have the time to show you, some of those code. Again, you can get fairly high speed up, okay, on F1. So these are the, just want to show that we can support different kind of applications. We are not just limited to image processing or deep learning. And also want to show you, so just show you the results for some kernels. Right? I want to show you the results for some more complex applications. So this is a fairly widely used computer vision algorithm, optical flow. The reason I want to show you this benchmark is this is where we actually need to do fairly complex data reuse. So we have a pipeline of filters, right? Also convolution kernels. So this is where we need to do data streaming, line buffers, and everything. And also, we actually need to do data reuse at the DRAM level as well, not just on-chip SRAM. So we actually need to buffer up like multiple image frames, video frames for this specific algorithm. Okay, so just want to show the code for hydroxyl. Again, it's a fairly clean code. So we can easily specify the convolution kernels. So compared to IWLS, right? So this is much more compact, right? Much more readable, much more retargetable. And the nice thing with HydroCL is that although I did not get a chance to introduce some of these primitives, we actually allow you to do efficient data placement as well. This is a .2 primitive. So this is where we can actually do the data reuse. So either on chip, okay? So combined with the reuse set, either on chip or off chip on DRAM. Okay? And we can also use the same interface to enable, the unified communication, right? So the way to specify communication between the host CPU and the FPGA, and also the communication between different sub-modules in the same accelerator, right? Okay, so this is this code is going to be released soon. Okay, again, HydroCL is actually open source project. It's a fairly young project, 1 year old, but we already actually getting a lot of interest, right? So from both academia and industry, so we have industry user as well. Hopefully, we'll have we'll be able to grow the community even more. So we already have a website. If you're interested, we have a website, with many interesting tutorial examples, for machine learning, like the ones that I showed you. And again, I hope that if you're interested, you'll be right. So later on, interested to collaborate and contribute as well. Okay, so all right, so I just talked about 3 things, right? This is a question I asked early on, right? Have you solved HLS in theory? Again, hopefully now you understand why I put, quotes, right, on this heavily overloaded terms, right? Theory, practice, or style. Obviously, my answer is not yet, right? So there are still a lot of interesting, exciting research that we can pursue, right, in each of these categories. So just want to name a few. So one thing that I did not get a chance to talk about is, in some cases, right, HLS may not give you the highest possible frequency, right? Because HLS may generate high fan-out interconnect high fan-out wires, right? So this is where HLS is actually at a disadvantage compared to RTL, because with RTL, you know the source code, right? You know where to pipeline, where to break that long wire, but you have to change the controller. Of course, that's not productive, right? But with HLS, since the generated source code is not that readable anymore, right? It may be hard to really figure out where's the long wire, how to break it. So this is where there are actually a lot of interesting research opportunities for physical aware HLS. This is one of the recent collaboration with Professor Jensen's Collins group, right? So this just presented at DAC. We show that for some of the complex benchmarks, if we actually find that, so there are actually just a few common cases of high fan-out interconnects from HLS. We can actually break them, pipeline them in a systematic way, so to increase the frequency by a lot. Okay, and also there's some ongoing work, right? So where we show that with HLS guided floor plan, we can again get a very significant timing improvement. Also, we can, in some cases, we can turn an unroutable design into a very much routable one. But this is actually where we need to co-design between HLS, also downstream tools, okay, including floor planning, including place and route. And also, what I talk about, right? So is we were talking about generating fixed function accelerators, right, from HLS. But there are also many exciting opportunities for generating programmable accelerators, right, for domain of applications, right? So this is one of the recent work that done by Guy. Okay, so he showed that for RISC-V based accelerators, that we can actually quickly generate many different kind of variations, right, varying the pipelining knobs and other knobs. So where we can actually get very competitive results against some of the widely used open source RISC-V implementations. We can also easily add new kind of co-processors as well with this kind of automation. And also another area that's not really heavily researched is on this sparse applications, for example, for graph or sparse linear algebra. So we also have some recent work that show that we can actually design speed up sparse applications, like tensor applications, so even sparse linear algebra application in a fairly efficient way. So I think architectures like this later on can be automatically generated as well. Okay, and also I really think that there's actually a lot of room to improve, right? So in terms of the program, for the program model, program abstraction for accelerated design, also for HLS. Okay, I showed you HeteroCL, right? So that's one example. We are also working with Intel on designing DSL. This DSL is actually not specific to one specific application, but this DSL is actually targeting, a broader class of systolic algorithms. Okay. So again, we have a similar flavor of decoupling of algorithm specification. So in this case, we have to use URE to specify the systolic algorithms, and also we can decouple spatial mappings in the same language as well. So this actually allows us to generate very high performance systolic arrays, okay, on the FPGA. Just want to show you some results, right? So the language that we developed is going to be presented at ICCAT soon. It's called SUSY. So we actually compare with some of the well-known accelerator languages. In this case, the spatial, they're not using a systolic algorithm. So that's why the very low throughput HeteroCL. We have an automatic way to generate systolic algorithms, but with SUSY, we can actually further customize the shape, spatial mapping of the systolic array for specific algorithm. So this is where we can actually get very high speed up, with a very few line count, okay, compared to Ninja. This is done by industry expert by, in 18 months. That's what I heard. Okay, so we already like within close to 90%. This is actually an ongoing project, and only using 3% of the code by using this kind of a decoupling, right, in the DSL. All right, so so just to conclude, right? So I really think that this is also a reason that I named the title that way. So I really think that so we are seeing the resurgence. We are really just seeing the beginning of widespread use of HLS for accelerated design, and this is actually going to generate many interesting new research problems, right? I think that there are still plenty of room, right, to improve at the core of HLS, right? I mentioned some of those, but the interaction of HLS with the downstream to like logic synthesis and place and route. So those are not actually well explored. There are some research in the past, but there are actually a lot more to be done. And also the sense of programmable accelerators and sense of secure accelerators, right? There are easily many interesting opportunities, right? Even at the core. And also I think there are actually even more room on the surface. So like really about the user interface of accelerator design or HLS. So again, I mentioned some examples, right? The language compiler, right, for DSLs, right, and also we are also interested in understanding the type system design, right? So really, if you think about there's a HLS synthesizer subset, right, based on either C, OpenCL, or Python, but there's really no HLS language, right? So there's really no type system design for HLS. So there's actually I have joint work with my colleague Adrian Sampson. So we have we just presented some work related to this direction at PLDI last month, and also I talked about these many sketching primitives, right? Customization primitives, right? Can we automate those, right? That's actually an open problem, or can we all integrate with auto tuning tools, right? And also the interface with higher DSLs like PyTorch, like TensorFlow, like some graph DSLs. This is also a very interesting topic to explore as well. Okay. All right. So I guess with that, I'm pretty much done. So of course, I want to acknowledge the sponsors, and this is really also this work is really the credits really go to the students, right, involved. This is actually a picture that we took at the Cayuga Lake last year. And this is unfortunately a picture from 2019, right? For obvious reason. So I really hope that we get to take a new picture soon, right? So I also want to briefly advertise that. So some of the students, Yuan, Jordan, and Ichi, so they're going to be presenting at the programming context session at 3 later this 3 p.m. Eastern later this afternoon. Hopefully many of you will attend that as well. All right, okay, so with that, I'm done. Thanks very much for your kind attention.